Hi IB, this is your third day of integration, and we have just talked about how integration is the opposite of differentiation. We also discussed in class the fundamental theorem of calculus, so we know that when you take the integral, you get the antiderivative, and when you take the derivative of the antiderivative, then you get back to the original function. So you're basically going in one big circle. Even though you guys can think through how to sort of take the antiderivative, because you're really doing everything we did in first quarter and part of second quarter in reverse, it's a little hard to think backwards sometimes. So we are going to neatly write up what the rules are for going backwards through different functions today, so you guys can have a nice, neat list of how to integrate different functions, all right? The very first one is a constant function. If you guys let c be a constant, so any number, 5, 6, 2, 1, whatever you want. If c is a constant, then when you take the antiderivative, you're going to get c times a variable. Remember, to check this, we would take the derivative. The derivative of cx would just be c. We're going to add on this constant because there could possibly have been a constant that when you took the derivative, it went to 0. So when we go backwards, we might have had a constant as part of our original function. So we don't have two c's though, we're calling this c1. And this is standing for our constant function. Because now this c turns into a coefficient, and now this c is a constant. Okay? The second function that we talked about in class was taking the integral of some base x with an exponent. Since when you guys took a derivative, you subtracted 1 from the exponent and then multiplied by that exponent, now we're going to do both of those steps in reverse. We're going to add 1 to the exponent and also divide by the exponent. So we're now going to take the n, the exponent, add 1 to it, and then also divide by the n plus 1. Again, we're going to add a constant because we might have had a constant that turned into 0 when you guys took the derivative. Third step, that's pretty easy, is when you guys take the antiderivative of an e, an exponential function. So we know the derivative of e is just e to the x. So when I take the antiderivative, it's also going to be e to the x. Normally, you would multiply by the derivative of the exponent. Well, since our derivative of the exponent is 1, it would be as if you're just dividing by 1 here. So that's not going to make a big difference. And then again, add on the c, add on your constant. The one that we really didn't go over in class is the 1 divided by x. Well, remember that this was our natural log. When you guys have a natural log function, when you took the derivative of natural log of x, then you get 1 over x. So if I did my little brain bubble over here on the side, if I take the derivative of the natural log of x, I would get 1 over x. So now that I'm going backwards, if I start with the integral of 1 over x right here, okay, when I take the antiderivative, I will get back to the natural log of x plus c. All right? So these are the 4 that are kind of the more straightforward ones. We only have x's. We're not talking about other functions. So when we say e to the x, it's really just e to the x. It's not e to the 2x plus 5. So now we're going to start looking at how can we do this, because they're not always going to be this cut and dry. So let's take a look at our first example. I'm going to scroll up a little bit for you. Okay? If you guys take the derivative of e to the 2x minus 1, you would keep e to the 2x minus 1, but then we would also multiply by the derivative of the exponent, which is 2 in this case. So I would get 2 times e to the 2x minus 1. So if I wanted to do this backwards, right, then I would want to, instead of multiplying by the derivative, if you guys come over here with me, I've got the integral of e to the 2x minus 1 dx. Instead of multiplying by that 2, because I'm going backwards, I'm going to divide by 2. So I get this 1/2 here in front. Okay, so the 1/2 is coming from 1 divided by the derivative of the exponent. So if I put this into basic rules, basic terms, I'm saying that the integral of e to the ax plus b would be 1 divided by a, because a is the derivative of the exponent. It's also the coefficient in this case, but it's the derivative of the exponent. And then I keep my regular e to the ax plus b because that's how e works. And then I'm going to add this constant c on the end. All right? So this is very similar to your rule number 3. Rule number 3 is very similar to rule number 5, but the 5 is a little different because your exponent is not just x anymore. It's going to be a different function. All right? Okay. Let's think about changing one other one. Let's call this rule 6. If you guys took the derivative of 2x plus 3 to the 4th power, so instead of just x to the 4th power, I now have a different function raised to the 4th power. When you guys take the derivative, I bring the 4 down. I will raise my 2x plus 3 to the 3rd power, and then I'll multiply by 2 because that's the derivative of the inside function. Remember this whole chain rule. So we're really just working through the chain rule right now. Okay? So let's think about that backwards. All right. If I'm going to go through this backwards, I am going to want to add 1 to the exponent. I'm going to keep the inside the same because that hasn't changed, but I'm going to want to divide by the derivative of my inside. So instead of multiplying by the derivative, I'm going to want to divide by it. So that would look like, let's see, 2x plus 3 raised to the 4th power, and I'm going to want to divide by the derivative of the inside, which is 2. So let's see, I'm going to add one more step in here. So 2x plus 3 raised to the 4th power. I want to divide by the derivative of the inside, but I not only want to divide by the derivative of the inside, I also want to divide by the exponent. Okay? Think back to rule number 2. Rule number 2 was just x raised to the nth power, and I want to divide by this exponent here, the n plus 1. So now that I have something raised to the nth power, come back over here for a minute, I'm going to also want to divide by the 4, my exponent. So I have a 1/2 and a 1/4, which makes 1/8. 2x plus 3 to the 4th power, and then I added the plus c onto it. All right? So in general terms, if I have the integral of a linear expression, remember this is a linear function here, ax plus b to the nth power, I'm going to not only divide by a, but I'm also going to divide by my exponent, n plus 1. And then simplify, of course. All right? So number 6 is very similar to rule number 2. 2 and 6 are both very similar. And last but not least, rule number 7 deals with the natural log. Let's think first to how I would take the derivative of a natural log. For natural log, we take the derivative of the inside, which is 2, and then I'm going to divide by the original inside, so 2x plus 1. So here's my derivative. If you guys come over here, now let's look at how I would do that backwards. If I have 1 over 2x plus 1, okay, the numerator should come from the derivative of the inside. My derivative of the inside should be 2. So there's a little bit of a miscommunication there between the numerator and the denominator. So let's see what happens. All right. I want to take the natural log of 2x plus 1, because I know that 1 divided by 2x plus 1, that backwards gives me the natural log function. All right? So my denominator is 2x plus 1, so that's what goes inside the natural log. However, the derivative of the inside is 2, and I didn't have a 2. I had a 1. So in order to not have a 2 there, I would have to multiply by 1 over 2, or divide by the derivative of the inside in order to get rid of it, because I didn't have it there in my original problem. All right, so instead of multiplying by the derivative of the inside, we're going to divide by the derivative of the inside. So in general terms, if you have the integral of 1 divided by ax plus b dx, you're going to wind up with the natural log of ax plus b divided by a, so I want to divide by that derivative of the inside function, and then add your c on the end. So rule number 7 is very similar to rule number 4. The only difference is that you have a more complex function than just x when you're dealing with number 7. But really the only difference in 5, 6, and 7 is that I have an a, which is a coefficient that also happens to be the derivative of the inside function, so I just want to divide by it. I want to get rid of it. So divide by it instead of multiplying by it like we did with differentiation. All right? So now what happens when these problems get a little bit trickier? All right, here's an example of one that's not as cut and dry. Not as cut and dry because if I look at the denominator and the numerator, I know I have a fraction, which makes me think of a natural log, because the fractions that we've done so far have either been a polynomial that I could rewrite or a natural log function. So I know it's going to have something to do with natural log. The problem is, though, the numerator is not necessarily the derivative of the denominator. It's close, but it's not necessarily the same. Very, very similar, though. So we're going to be able to use that to our advantage with a little game of substitution. So I'm going to use our favorite letter so far this year has been U. We've used it with many of our other rules. We're going to use U substitution. And all we're going to do is say, well, I know that U is, we're going to let U be our denominator. So x cubed plus 2x. Okay? The deal is now, if I take the derivative of U with respect to x, so du with respect to x, because x is our inside function here, I'm going to get 3x squared plus 2x, plus 2, excuse me. Okay? Again, this looks really, really close to what I have over there in my problem. I'm going to multiply by this dx, which is going to give me du. And now I have 3x squared plus 2 dx. Okay. If I look back to my problem, I don't have a du. I have a dx. And if I'm playing a game of substitution, I need to substitute what I have. So I have dx. That means I want to isolate dx. In order to isolate dx, I'm going to divide by 3x squared plus 2. Okay, so now I can actually substitute du divided by 3x squared plus 2 into dx. I can also substitute x cubed plus 2x, my denominator. That was u. So I'm going to say this is u. And I'm going to substitute in 6x squared plus 4 divided by u. And then my dx is down here, which is du over 3x squared plus 2. All right. Of course, our favorite thing once we substitute is to simplify. If I rewrite, I can cross out 3x squared plus 2, which leaves me with 2 divided by u du. I can also pull out my constant 2, and then 1 over u becomes ln of u.